When engineers first claimed that the future of batteries was salt, people laughed at them. Not metaphorically, literally, colleagues shrugged at conferences, investors closed their laptops. And then the largest battery contract in human history was signed, and at its core was exactly that element. The same one you sprinkle on your food every day. How did that happen? And why did the entire world sleep through this moment for 20 years? We're talking about an order for 60 gigawatt hours of sodium-ion batteries. To put that in perspective, that's enough energy to simultaneously charge every smartphone on the planet. The order wasn't placed by a venture-backed startup or a university lab. It was signed by the largest battery manufacturer in the world, a company that understands what's happening with lithium better than any other player, and one that bet on something different. To understand why this decision matters so much, you first need to understand how we ended up addicted to lithium in the first place. Right now, as you're watching this video, a lithium battery is within arm's reach. Your phone, your laptop, your electric car, your wireless earbuds. Lithium-ion technology has become so deeply embedded in everyday life that most people stopped asking a long time ago, is there something better? Before lithium, devices ran on nickel-cadmium batteries, heavy, bulky, with a negligible energy capacity. The shift to lithium-ion technology in the early 90s wasn't just an improvement, it was a complete reimagining of what a battery could be. Energy density increased roughly 3 times compared to its predecessors. Devices became lighter, more compact, and more powerful all at once. The smartphone as we know it today simply wouldn't exist without that transition. The basic principle behind any battery is straightforward. Inside there are 2 poles and a liquid between them that carries charged particles back and forth. During charging, the particles are forced from one pole to the other. During use, they return, generating electricity. Lithium worked exceptionally well for 2 reasons. It's one of the lightest elements on the periodic table, which allows an enormous number of particles to be packed into a small volume, and it has a high potential for transferring current. For 3 decades, nothing could seriously compete with it. But that's exactly when something works too well for too long. The cracks in the foundation start quietly growing. In 2016, the world's largest consumer electronics manufacturer released a flagship smartphone to glowing reviews and record pre-orders. Within a few weeks, the phones started catching fire, in pockets, on airplanes, on nightstands. Airlines banned the device from flights. The entire product line was recalled. Losses totaled $5 billion. The failure went down in consumer electronics history as one of the most spectacular ever. But here's what most observers missed. This wasn't just an engineering miscalculation by one company. Yes, specific design errors were made, but the hidden danger had always been there. In every lithium battery ever released into the world. The liquid inside a lithium battery that carries the charged particles is made up of organic solvents. They are flammable by nature. Overheating, physical damage, overcharging, and the liquid ignites. When one cell catches fire, it heats the neighboring cells. Those ignite too, and the chain reaction spreads like dominoes. Today, in one of the world's largest cities, fires caused by lithium batteries have become the leading cause of fatal blazes. Not a statistic from the last decade, this is reality right now. There's another problem that gets far less attention: cold. At low temperatures, the charged particles inside a lithium battery stop moving smoothly and begin depositing on internal surfaces in the form of tiny metallic needles. Over time, these needles can short-circuit the 2 poles from the inside, and an internal short circuit in a lithium battery means rapid overheating. Even when it doesn't reach a short circuit, the losses in cold weather are enormous. At temperatures around freezing, a lithium battery loses between 20 and 40% of its range. For people living in northern regions, that means losing 100 kilometers on a cold morning, exactly when they need it most. Engineers knew about these problems. They worked around them with cooling systems and smart software, but the chemistry itself never changed. And the reason it didn't change has nothing to do with science. It's about money and geography. 3 countries control 90% of the world's lithium production. One of them processes around 65% of that raw material into battery-grade material and manufactures roughly 3/4 of all lithium-ion batteries on the planet. Most of the world's electric vehicles, smartphones, and energy storage systems depend on a supply chain concentrated in a very small number of points on the map. From 2020 to 2022, the price of key lithium raw materials increased eightfold, not 8%, 8 times in just 2 years. Then in 2023, the market reversed sharply. Prices collapsed by more than 70% in a single year. Companies that had locked in long-term contracts at the peak suddenly found themselves trapped paying a price that had long since stopped reflecting reality. An entire industry had built its business around a raw material that behaved like a speculative asset, unpredictable and beyond the control of manufacturers. That's the moment the world remembered sodium. The history of sodium batteries actually predates lithium batteries. Back in the 1960s, scientists were already looking at sodium as the basis for rechargeable batteries. It sits right next to lithium on the periodic table, behaves in a chemically similar way, and is one of the most abundant elements on Earth. The first high-energy rechargeable battery created by a major automaker in 1966 ran on sodium, but it had a fatal flaw. It required an operating temperature of around 300 degrees Celsius, hot enough to melt lead. A brilliant concept, with zero practical application. In 1972, a researcher named Stanley Whittingham developed a lithium battery that worked at room temperature. Lithium got a massive head start, and nearly all the world's research funding chased after it. In 1991, the first commercial lithium-ion battery was released, and since then, more than $1 trillion have been invested in that technology. Sodium was left behind, not because it was inferior, but because all the momentum was pointing in the other direction. There was also a specific technical problem. Sodium particles are roughly 35% larger than lithium particles. Graphite, the material in which lithium is stored inside a battery, has tightly ordered layers. Lithium particles slip in and out of those layers thousands of times without damage. Sodium particles are too big. Each charge cycle pushed the layers apart and irreversibly damaged the structure. After a few hundred cycles, the battery was unusable. That single materials problem kept sodium out of commercial use for more than 40 years, until a research team in 2000 discovered hard carbon. Regular graphite is like a perfectly stacked deck of cards, neat, parallel layers. Hard carbon is different. It's produced by heating organic materials, plant waste, biomass, glucose, to temperatures between 1,000 and 1,400 degrees Celsius in a sealed environment without oxygen. The carbon atoms lock into a disordered structure full of irregular gaps and micropores. These gaps are large enough and varied enough to hold sodium particles without destroying the structure through repeated charge cycles. For the first time, sodium had a host material capable of surviving thousands of cycles. But between a scientific breakthrough and a commercial product, there's a massive gap. Hard carbon acts like a sponge. It readily absorbs moisture from the air. Even a tiny amount of water inside a cell reacts with the electrolyte and slowly destroys the battery from the inside. The world's largest battery manufacturer invested around $1.5 billion over 10 years to solve this problem. The first solution involved modifying the surface chemistry of the hard carbon. The parts that attracted water were replaced with compounds that actively repel it. The second involved controlling the size of the internal pores during manufacturing to within 1 angstrom, that's 1/10 billionth of a meter. Pores too small, and sodium particles can't enter efficiently. Too large, and capacity is lost. Finding the right balance for mass production took years of work that most companies simply weren't prepared to put in. The result is a battery with specs that would have seemed impossible for sodium technology not long ago. It delivers 175 watt-hours per kilogram, a figure comparable to the lithium iron phosphate batteries used today in most affordable electric vehicles. In a real car, that translates to more than 500 kilometers on a single charge, with charging to 80% taking 15 minutes. Not lab numbers, production numbers. For mass manufacturing, the cycle life is even more impressive. The battery withstands more than 10,000 full charge-discharge cycles before significant degradation, roughly 3 times more than competing lithium cells. With daily charging, such a battery would remain functional for more than 27 years. In cold conditions, sodium goes from impressive to genuinely outstanding. The electrolyte stays liquid at temperatures down to -58 degrees Celsius. At that level of cold, the battery retains 90% of its full capacity. A lithium battery at the same temperature barely functions. For electric vehicles in northern climates, that's the difference between a car that works reliably in winter and one that loses a third of its range on a cold morning. The price point locks in the advantage. Sodium-ion cells are manufactured at around $19 per kilowatt-hour. Lithium-ion cells typically cost between $55 and $70 per kilowatt-hour. That's not a small gap. And unlike lithium, sodium, and aluminum are globally abundant materials. The supply chain isn't concentrated in a handful of countries, which means stable and predictable pricing for everyone in the market. Does this mean the end of lithium? No. Sodium-ion batteries have one limitation they're unlikely to fully escape: energy density. Sodium particles are heavier and larger than lithium particles, which means there's a ceiling on how much energy can be packed into a unit of weight. For electric aviation, where every extra gram costs range, that's a fundamental issue. For consumer electronics, where a battery has to fit inside a smartphone body, lithium will likely remain dominant for a long time to come. The world's largest manufacturer is moving toward a different scenario, not replacing one chemistry with another, but making them partners. A battery pack for an electric vehicle has already been developed that's divided into two zones: one sodium, one lithium. Software decides in real time which zone to draw energy from, based on temperature, speed, and charge level. It's cold and lithium is struggling. Sodium takes the load. Long highway drive, maximum range needed. Lithium kicks in. Neither chemistry is pushed to its limits. Both are used exactly where they perform best. The 60 gigawatt-hour order fits perfectly into this picture. Over the entire previous year, the same manufacturer shipped around 122 gigawatt-hours of energy storage batteries in total. A single sodium order represents roughly half of that annual volume for a technology that didn't exist in commercial production just 12 months earlier. And there's an important lesson here worth sitting with. The research proving that hard carbon could store sodium ions was published in 2000. The technology had been ready for large-scale application for a long time. But serious investment and attention from major players didn't flow toward sodium until 2022, almost exactly when lithium prices exploded. Lithium's problems were never a secret. They had been documented for decades. But when a dominant technology works well enough and the profits keep flowing, the industry doesn't go looking for something better. It takes a shock. It takes a moment when the cost of doing nothing finally outweighs the comfort of the familiar. The sodium-ion battery didn't come out of nowhere. It was waiting in laboratories and scientific publications for more than 20 years, waiting until the world was ready. And lithium itself brought that moment closer by becoming too expensive, too volatile, and too geographically vulnerable to keep ignoring the alternative. If you're into stories like this about technologies that are quietly changing the world, hit like and subscribe to the channel so you don't miss the next one. Turn on notifications, we post regularly, and drop a comment below. Do you think sodium will replace lithium in your lifetime? Or does lithium still have enough fight left in it?